Hello, everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Rula Deeb. I'm a principal at Geosyntac Consultants in Oakland and the coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of SERDP and ESTCP by Kara Patton, followed by a list of upcoming webinars in the webinar series. After Kara's opening remarks, we will transition to the technical portion of the webinar. Today's event features two presentations on watershed assessment and stormwater management optimization tools. First, Dr. David Goodrich will talk about watershed modeling and assessment to sustain and enhance military mission and training. His presentation will be followed by a brief Q&A session. Second, Ms. Heidi Howard will discuss recent optimization efforts of a stormwater modeling approach, and she will be followed by a second Q&A session. We will conclude the webinar with an interactive Q&A session, including both of our speakers. Today's broadcast will be listen-only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions well in advance of that session. On this slide, we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen. You may also call into the conference line if you have problems with the computer audio. If you continue to have issues, please submit a comment using the chat box in the lower left corner of your screen. With that, I would like to introduce Ms. Kara Patton from HGL. Kara has supported SERDP and ESTCP for 8 years. She has worked with both the Environmental Restoration Program area and the Resource Conservation and Climate Change Program area. She has also provided general contract management support for the program office. Currently, Kara provides technical and programmatic support for the Resource Conservation and Climate Change Program area, which is really the topic of today's webinar. And with that, I turn it over to you, Kara.
Thank you, Rula. I'm happy to welcome everyone to SERDP and ESTCP's webinar today. SERDP is a Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD and environmental requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate and validate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies and methodologies from the research phase to a demonstration of cost and performance at the field scale. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. There are 4 program areas in SERDP, 5 in ESTCP. The Energy and Water Program area is only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Climate Change, and Weapon Systems and Platforms, are SERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focusing on demonstrations that are being conducted under the Resource Conservation and Climate Change program area. Resource conservation and climate change has essentially 3 main areas of research: natural resources, climate change, and air quality. Today's webinar is on watershed and stormwater modeling innovations. Our webinar series will be highlighting research and demonstration efforts from each of the 5 program areas. As you can see, our webinars will cover a broad range of topics, with upcoming topics covering vapor intrusion, to water conservation, to military aircraft and equipment coatings. The next webinar based on research and demonstrations under Resource Conservation and Climate Change will be on April 7th. You can find more information about upcoming webinars on the SERDP and ESTCP website. Registration will be live for the next webinar in the coming weeks. I hope you enjoy the webinar today.
Thank you, Cara. It is now my pleasure to introduce our first speaker, Dr. David Goodrich, who is a lead scientist and research hydraulic engineer with the USDA's Agricultural Research Service at the Southwest Water Research Center in Tucson, Arizona. Dave has been with the USDA since 1988, and he also serves as an associate adjunct professor in the Department of Hydrology and Water Resources at the University of Arizona. Dave's current research efforts are directed to scaling issues in rainfall runoff and erosion modeling, identification of dominant hydrologic processes over a range of basin scales, climatic change impacts on hydrologic response, and the incorporation of remotely sensed data into hydrologic models. And with that, I turn it over to you, Dave.
Thank you very much for the introduction, Rula. Today, I'd like to talk again about watershed modeling and assessment to sustain and enhance military mission. In terms of just an overview of the talk, give a little bit of motivation of why this is important and will be important to military installations, give you a little bit of background about hydrology and watershed modeling, and then specifically talk about some model calibration, validation, and uncertainty issues, both in the context of available observations and also in the context of what the model decisions or what decisions will be made based on model outputs and scenarios. And then I'm representing not only the project I'm involved in, but also two other ESTCP projects. By the PIs on those are Tony Denosian and Billy Johnson. And we'll give a little overview of those projects later on in the presentation and finally conclude. So in terms of motivation, DOD manages approximately 30 million acres of land, and training and mission requirements, particularly heavy vehicle training, impact land cover, erosion, flooding, and water quality. And in terms of stewardship, compliance, and sustainability, those impacts have to be managed, requirements from NEPA as well as the Clean Water Act. And the DOD rule that's listed here specifically states that a watershed-based management approach be taken. And that's really to try to minimize the impacts to wetlands, groundwater, and surface waters, both on the installation and adjacent to the installation. Particular implications that are called out in the Clean Water Act of Section 303D have to do with impaired water. So if a body of water is polluted beyond a particular water quality standard, it's listed as impaired. And for impaired waters, it's required to develop a TMDL, or a total maximum daily load. And this is the maximum amount of a pollutant that a water body can receive and still safely meet the water quality standard. So, having to do and try to get waters off the impaired list can trigger possible training and land use management restrictions. So it's important that we try not to impair downstream waters. So in terms of watershed monitoring and modeling, to really assess the impacts of missions and training activities, it can require, and I would argue requires, both monitoring and modeling. Monitoring is typically labor intensive. It typically has to go on for an extended period of time to capture a range of hydroclimatic conditions. So if we can develop models that are verified, we can complement the monitoring activities to allow evaluations of impacts, and also play scenarios in terms of, let's say you want to open up a training area, a new training area. Are there areas that you can identify with the model that may be at particular risk that might be avoided, whether it be habitat, excessive erosion, etc.? So just a quick little bit of hydrology background. So a simple water balance can be written as shown in the blue box. So, runoff equals precipitation minus the amount of water that infiltrates into the soil, less evapotranspiration, that's evaporation from the soils, as well as transpiration of water through the plants, and change in storage of water resources, whether it be in the groundwater or in the pore space of soils. So infiltration is a function of a number of things, not only the soil and its properties, but particularly land use, land cover, things like compaction that may occur after heavy training activities, and soil moisture. And similarly, evaporation or evapotranspiration is a function of the weather, soils, plants, land use, and soil moisture. So the models that we develop are an attempt to represent these processes, using sets of mathematical equations or empirical relationships. So we're trying to capture what goes on the watershed that may impact rainfall runoff relationships and subsequent things like erosion and water quality. So there's a lot of different kind of models around, but the models in the three projects that I'm representing in this talk are deterministic models, meaning that if you put in the same inputs into the model, you'll get the same outputs. It's not a stochastic representation. And the models either employ fundamental laws like conservation of mass and energy, or they may involve some empirical relationships established by examining input-out relationships, and that gives you a hybrid model. They're distributed in space, meaning that we typically try to break the watershed up. The little area over here that we see to the right is just a representation of a watershed that's broken up into contributing areas to stream segments. So this discretization of the watershed is an attempt to capture the variability that you often see in watersheds, whether it, again, be land use or different vegetation types, different soils, etc. And the typical data that you need for a distributed watershed model is, much of it is nationally available. So again, you really have to characterize the watershed properly to get the processes right and get the relationships right. So a common one, we need topography. Obviously, water flows faster on steeper slopes, and we have nationally available 10 meter to 30 meter DEM data. Aerial LiDAR data, which can be much finer resolution, can also be used in these modeling efforts. Soils data is provided typically by the U.S. Department of Agriculture, and the StatsGo database is a coarser database, and SERDP is a finer or a higher resolution database, and they have set fields in them with typical soil properties, and these things can be read into your models to help parameterize them. Globally, we can use FAO or Food and Agricultural Organization soils, and those are typically sort of at the scale of the StatsGo work. Land use, land cover data is available both from the USGS as well as NASA, and NLCD is the National Land Cover Data Set. REGAP is a different type of land classification. But one important thing to note is that these land cover classes typically don't tell you the condition of the land. In other words, it could be classified as a grassland, but you don't know if that grassland may be grazed down to the ground or a meter-high stand of very thick grass. We need drivers, precipitation, and weather. If we're not using design storms, so design storms have been developed by NOAA, and those are basically a typical storm size using historical data that's been developed to say what's the typical amount of rain that may fall in a 10 or a 24-hour period or a 1-hour period that may on average occur over 10 years, 5 years, etc. So these are used in engineering commonly to size culverts, bridge crossings, and that sort of thing. But one point I want to make, and we'll talk about it more later, is how important it is to have good rainfall data. If you're going to use local observations, they really need to be quite good in both time and space. And Weather Service radar fills some of that role, but again, we'll see how important that is in the future in the near coming slides. Now, management information. We need to know, again, this must be provided by the users with local knowledge. We've got an example here of information on the left, or an image on the left from the Pinyon Canyon Maneuver Site in southeastern Colorado, and they had brigade level training in June of 15. So the image on the left is before. The image on the right is after the training, and we can see a number of areas that were impacted by the training. And again, part of what we're trying to determine is, with our models as well as ground observations, how those training activities may impact things like erosion and runoff, and then subsequently how we might mitigate those activities. So a little bit more about approximations in watershed modeling. When we discretize a watershed, we typically then average the properties in those particular pieces. So we are averaging over a particular scale, so the parameters like infiltration, hydraulic roughness, are representing intersections of those data sets we just talked about, the topography, soils, and land cover. So there's an information loss as a function of geometric complexity. So if you have few elements, you're averaging over a much larger area. More elements, you try to isolate particular things with more detailed information. So there's definitely scaling issues involved here. And we typically compute the parameters for the model, again, infiltration type parameters, as a function of weighted averages, both in space and in depth for the example in soils. So on the bottom there, these watershed modeling relies on sort of condensing this spatial data into appropriate units for representing processes. Because of these approximations, to do, in my opinion, really quantitative modeling, we do need calibration data and observational data to say, are these models really reflecting reality? So model calibration and validation is a process where we're comparing model predictions to observations. And the first line up there is the one old saw about modeling. In fact, that all models are wrong, but some are useful. So again, don't use these models as tools to help you make more informed decisions. They are not going to give you perfect predictions by any means. So in terms of calibration and validation, we want to provide some confidence, though, that the models are making useful predictions. Now, we'll talk about what useful implies, and the community is working on this, again, for better communication to the user community. So for the example here, we'll have a runoff event, and we'll have a model predicted flow, and we'll have an observed flow. And there are a bunch of different metrics or statistics that can be computed where you're comparing the observed to the modeled. And again, these are some common ones: an Ash-Sutcliffe efficiency statistic. Your model is perfect, that number will be 1. A bias statistic, as well as a relative root mean square error. And this is one set of tools to evaluate models, but we should use graphics, we should look at outliers, and also examine the data carefully for what may be spurious observations, because there is uncertainty in the observational data as well. And so the model accuracy is really dependent on many factors. First is you conceptualize the processes properly. In other words, if you're modeling, in a flat runoff situation like Florida, and your processes and your representations are much more snow-dominated or oriented, you're just starting from the wrong place. Again, we need high-quality precipitation data, both in time and space, and we need to characterize the watershed well. Now, model sensitivity and variance analysis is used typically to try to identify those model parameters that are highly sensitive. So if you've got high uncertainty in the highly sensitive parameters, you're going to impart substantial uncertainty into the model predictions. And that's illustrated in this following slide. So this is the Taylor watershed at the Pinyon Canyon Maneuver Site. The isoheights you see here are total rainfall depths for an event on October 11th, 2008. And so we're showing over here the hydrographs, or the rainfall intensity as a function of time, by using 6 rain gauges. So the red dots here are available on-the-ground observations from rain gauges compared to a single rain gauge at the outlet. So if you use all that information in a space-time weighting of the 6 rain gauges, you'll get this model prediction in blue. If you use just the single gauge that's at the outlet, you'll get this prediction. And again, great difference, but you can see that the variability of the rainfall depth is substantial over this watershed. It's not a very large watershed, about 50 square miles. So you need that spatial rainfall information to get good model predictions. And that can be seen in some analysis in this next slide of variance analysis. So this was done on the experimental watershed that our group operates in southeastern Arizona. So it's a small watershed, 6.5 square kilometers. And this analysis was set up using Monte Carlo simulations, about 100,000, to explore the sensitivity and the invariance imparted by 23 different parameters, as well as some of the inputs. So basically what you see here is a response or a variance impact characteristic from 0 to 1. One's got a much higher influence. And if we look over here on the right, the rainfall depth bias is by far the dominant factor in terms of the influence on sensitivity to peak runoff estimates. So if you don't get the rainfall right, it really doesn't matter how well you do on many of the other parameters. And second in line is infiltration, we see here, and then hydraulic roughness. So, what I advise, and many people advise, if you have to spend some money, buy some rain gauges. And again, as I say, radar rainfall information is helping in this regard, but in the western U.S., there's often blockage of radar information from mountains. Now, there are other products that are being developed to get around this, but for modeling at this sort of scale, rain gauges is very important, and good rain gauges. In terms of some technical progress, in terms of characterization issues, this is the same Taylor watershed. And if you just use those national data sets, you may not know that there are 111 erosion control dams, which are basically these small earthen structures that are really designed to capture erosion that's produced from training activities. So this little simulation shows that if you don't incorporate that local knowledge or information, again, this will significantly affect your model runoff results. So the red one is without any of these 111 erosion control dams, and the blue one is the simulation if you do represent these 111 dams. So again, you have to characterize the watershed not only with this nationally available information, but with locally available knowledge. So this concept comes up about model usefulness and objectives, and they're intertwined. So the usefulness really depends on what you're asking of the model or how you might be using model results for decision making. And there's sort of three general categories. An exploratory sense. You may want to make initial comparisons. This may be done with beta model development. And you're trying to see, is the model really getting the trends and directions correct? If it's not, and if it's not conserving mass, let's say, there's something wrong. You're either mischaracterizing the processes, or you've got, programming errors. From a planning context, you may want to use a model to rank relative priorities. In other words, you don't necessarily need to know the discharge at a particular point, but you may want to say this area of a watershed is more at risk for erosion than another area, so I'm either going to avoid training in that area, or if I do train, I'm going to take particular efforts for reseeding and for mitigating possible training impacts. Now, from a regulatory or legal standpoint, or human health may be involved, you do require model accuracy. And this, again, is where it's much more important to get the best quantitative estimates that the model can provide. And again, this means you have to have good data for calibration and validation. So again, there's an interplay between modeling and modeling. And the footnote on the bottom is just saying these aren't really, cut and dried categories. They do overlap, and there's professional judgment that's necessary and involved as well. So Harmel et al., 2014, is a paper summarized by a committee of modelers with the American Society of Biological and Agricultural Engineers. And they're trying to use this context about usefulness and model accuracy, model uncertainty, as well as measurement uncertainty to say what you might be able to have some confidence in using these models for. So in a best case, if we look at this just relative graph over here, if we have good model accuracy, low model uncertainty, and low measurement uncertainty, we're in our best case scenario. And we can think about using our model then for all three of the categories, exploratory, planning, as well as regulatory uses. Now, if we go to these other cases, for example, an intermediate case where we have good model accuracy, but we have high measurement uncertainty, we may want to be using this model that more from an exploratory or a planning standpoint. But the fact that we have high measurement uncertainty, we need to report those things to the users of the model and the decision makers and consider getting additional data. And because of that high uncertainty, this is really probably an inappropriate use from a regulatory or a legal standpoint. And in the weakest case, where we've got low accuracy in both the model measurement and model uncertainty, it may be low, but this reduces our confidence in prediction. So again, probably okay for exploratory uses, but probably inappropriate for planning and regulatory uses. So this sort of thing says you need to go back to the drawing board and either refine the model or potentially take and select a more appropriate model. Let's see, next slide. So overview, so there are three projects that I'm trying to represent in this presentation, but a common objective we're trying to evaluate in all three of these projects is the worth of data and observations for improving model accuracy and reducing uncertainty. And again, this is sort of telling you where should you put your efforts and your money. Should you buy more rain gauges? Should you do more runoff and water quality sampling? So again, the titles of the three projects are listed here. Again, Tony Donosian is the PI on the first project, and they're using three different models. So Basins is a model that was developed related to EPA efforts, specifically for TNDL modeling, and it's been modified and enhanced for military-specific applications. HPSF, for the Hydrologic Simulation Program Fortran, again, is another watershed-based model that's being coupled with a river analysis system, or HEC-RAS, to again see how much improvement the complex riverine model may add to a watershed model that doesn't represent the channel processes as accurately. Our group is got the automated geospatial watershed assessment system, and we're coupling that with a decision support tool that allows you to look into other things like economics, availability of training, and to weight those things as well as the model results to help in your decision making. So the technical objectives of the different models are listed here. And again, this is the Tony Denogian model, the basins model, and trying to look at demonstrating and validating the system that's been enhanced for military installation. The demonstration areas this is being applied to are Fort Benning and Fort A.P. Hill in Virginia, again, a more humid environment. Billy Johnson's project is, again, demonstrating and validating this linked riverine system to the watershed modeling system. Their project's demonstration sites are in Fort Hood as well in the Calligas Creek watershed in California. So a combination of semi-arid to more Mediterranean climate. Our particular demonstration sites are more arid and semi-arid in the Pinyon Canyon Maneuver Site in southeast Colorado, Fort Bliss, Texas and New Mexico, as well as Fort Carson in Colorado. So just an overview. I should stress, too, that our projects are in midstream. So we don't have final results yet, and this sort of just is a listing of where we're at right now. And 2 additional demonstration sites are being considered for both Tony and Billy's projects to try to cover some more hydroclimatic regions. Just some preliminary results from the initial demonstrations that have been done. We do know that training can have significant impacts on runoff and water quality, both locally and off base, which again might result in some regulatory restrictions. Preserving and expanding the training mission requires informed watershed management. And again, we can run scenarios if we develop some confidence in these models to help us make those decisions or help pick new training areas or rest existing training areas. We do have to incorporate local knowledge, such as the erosion control dams that we saw. And again, we're evaluating data richness versus model performance. And Tony's project had indicated that, blind model validation was only partially successful in that adding new observations did impart some model performance, but only if it was incorporated in a structured way. And again, as we saw, accuracy of precipitation data is critical to model success. So there's this trade-off then, or we're looking at what greater investments and observations, particularly precipitation and stream flow, is warranted at sparse gauged installations, predictions and management. So, for example, the Pinyon Canyon Maneuver Site that we're working at does have a relatively rich history, so we can look at removing observations to look at the degradation in model results as we remove that observational information to tell us what is the worth of these observations. So again, can we use models effectively to identify areas at risk for, let's say, excessive flooding and erosion, and then target mitigation efforts? So that's the wrap up for my portion of the talk. Contact information is shown on this slide, and I will turn it back over to Rula.
Wonderful. Thank you, Dave, for a very informative presentation. We have received a number of questions for you. Can you please tell us what watershed model was used for the study presented?
Well, again, there's 3 different models. In the Agua system, there is the Kinneros model and the SWAT model. And I know these terms may not mean anything to people, but there are, these are well-developed and established models that, there's typically each of them has their own website, so you can find background information. In Tony's project, they're using the Basins model that's been modified to help capture military training activities. And then 2 models are being coupled in Billy Johnson's project, the HPSF model, which is a watershed model, and the HEC-RAS riverine model, which is much more specifically geared toward modeling flow in channel systems.
Thank you, Dave. And can you tell us, for the 3 projects, why these 3, and is there a better model to use, or are they site-specific? Can you sort of elaborate on the differences between the 3 watershed models that are being used across the 3 projects?
Well, there's a lot of different models out there, and it's hard to judge which model may be better unless you specifically test them side to side. And part of that is due to the fact that some models are conceptualized in a different way and represent different processes by or that representation may have been built up by observations. They may be more appropriate to humid regions, let's say snow-dominated regions, or wet regions. So it's not an easy task to say this model will be the best. There's no one model that's necessarily best for an individual area. And again, that gets back to why you do need at least some observational data to say that whatever model you're using is reflecting reality. And you need to test it. And the reason there's probably different model applications at different areas is that the teams proposing these projects, they have familiarity with one model or another.
Great, thank you. For the bases that you have worked on, Dave, how do the natural resource and land managers envision using these modeling tools?
In the case of the Pinyon Canyon maneuver site, they want to know where to put in more of these erosion control structures. They want to potentially ask the question about, should I potentially rest an area from training? In other words, how long after a training, even if they do reseeding and mitigation, might it take to get back to a decent cover condition so that you can go back and train without really doing a lot of damage? So those are 2 particular examples. I know in Fort Hood on Billy Johnson's project, they were assessing they were using rock check dams and where to put them and how many of them to put in to reduce gully and channel head cutting.
Great, thank you. Can you comment on the difficulty of setting up and using these watershed models on the DoD installations?
It depends on how, there's been a big push in hydrologic modeling to couple them with geographic information systems so that you can automatically take things like these soils databases, the topography, land cover data layers, and do the initial setup and automatically, figure out what the drainage ways are, the drainage paths, the direction of water flow. So that's helped a great deal. There's, once you get beyond that, though, again, how do you incorporate that? The local knowledge is the part that's, more labor intensive, if you will, of capturing that local knowledge. But to do a good job, you do need to incorporate that. We can set up a watershed model with Agua in literally a half an hour if we have these data sets readily at hand. And we conduct, as well as the other projects, will conduct training sessions for the particular land resource managers at these bases to go through this process. And in fact, part of the demonstration is to ask that question for a person that's a natural resource manager that may have GIS skills. How long will it take them to set up these models, as well as have the confidence to, let's say, incorporate a new scenario and say, I'm going to put training in over in this region. So I'm going to change the properties of this region, and I'm going to rerun the model and see what the differences are. So it's not trivial, but it's doable with, again, some training for individual land resource managers on the installations.
Great, thank you. A question from Colorado State University. What was the resolution of the LIDAR data used to identify EC structures, and are you concerned that about a third of the EC structures were not identified?
We are. So the date of the LIDAR acquisition, I think, was in 2006. And however, we do have, or at least for the more modern or the more recent EC control dams, they do have design specs on how these were built. What we did is we knew the location. I'm sorry, back to the first part of the question. Resolution was 1 meter, basically, from 5 to 10 points per meter. And so when we didn't have an EC structure identified by LIDAR, they did have a shapefile, though, to say one was constructed there. So if we didn't have construction plans, we basically tried to get the general shape and characteristics of the EC dam and put it in that place. So again, it's not perfect, but it's better than not representing it at all.
Thank you. You mentioned HSPF cover sediment erosion, but does it do so for transport and deposition too? This is a question from Fort Drum, and they are interested in being a subject installation. We'll send you the contact information so you can reach out to the installation. But if you could please answer the question, Dave, about the cover sediment erosion.
There are functions for, I guess I'm interpreting cover and sediment erosion for upland erosion. The HEC-RAS system actually does a better job in the channels than, so it's the coupled system. But yes, HPSF does try to represent erosion from upland areas where cover may be impacted. And yeah, we'd be glad. And again, I'm not the lead on HPSF project, but we'd be glad to get the information to Billy Johnson, who is the lead on that.
Wonderful, thank you. And for those of you that are interested in fact sheets on these projects, you could search on the SERDP ESTCP website using the project numbers that Dave kindly referenced in his presentation. And a PDF of the slides is already available on the webinar webpage for download. One last question, Dave, before we move on to Heidi. From the Forest Service, which, in your opinion, which model is more suitable and accurate for capturing hydrology of low gradient coastal watersheds where there are also military installations?
That's not my area of expertise. I would lean more toward the basins or the HPSF model. Again, if they've been calibrated in those systems.
Great. Thank you again, Dave, for a great presentation and a wonderful Q&A session. It is now time to move on to our second presenter, who is Heidi Howard. Heidi is a research agronomist for military lands with the Army's Engineer Research and Development Center at the Construction Engineering Research Laboratory in Champaign, Illinois. Heidi is the program lead for the development of methodologies and algorithms for quantifying cumulative interactions of land management and military systems on training land. This includes the development, validation, and implementation of stormwater and erosion control management designs, military vehicle impact models, vehicle impact assessment, and vegetation recovery. Ms. Howard is also responsible for research on sustainable lands and ranges for military installations. She holds a BS in biology from Western Illinois University and an MS in natural resources and environmental sciences from the University of Illinois. And with that, I turn it over to you, Heidi.
Well, thank you. Dave actually did an awesome job of kind of laying the foundation for some of the work that I'll be talking about. So thank you, Dave. Firstly, I need to acknowledge my co-author on this, and that's Chad Hemley from Tetra Tech. And actually, Tetra Tech and the Air Force AFCEC were the primary leads on this project prior to it going ESTCP for validation. So I'll go over our agenda for today, and we're going to do a little discussion on ESA 438, why we have these concerns regarding model selection tools for compliance with ESA 438, the modeling approaches that are approved in by EPA, how the model selection tool that we're in development and validation for, how it came about, what it does, our preliminary results for it, and then the usefulness and LID applications of the tool, basically step number 2. Like Dave indicated that we're midstream in this process. The MST has not been validated across all climate regions as of now. We're in that process. I'll talk more on that. And but we can go and make it available to the installations or others at this point with the knowledge that it is still in development. Okay, and finally we'll go over our conclusions. So the motivation behind this was ESA 438. ESA 438 came out in 2007 because we have an increasing stringent stormwater regulations that are created in response to our adverse impacts caused by conversion of pervious surfaces to impervious surfaces. And the DoD are being faced with the daunting task of building and maintaining stormwater best management practices to comply with applicable regulations in a limited budget. Specifically, like we said, ESA, the Energy Independence and Security Act, Section 438, which is the stormwater regulation that's applicable to all DoD installations, and it has a requirement for modeling to determine sizing of BMPs for compliance. And part of that is you must meet pre-hydraulic conditions post-construction. And you need to utilize low-impact development best management practices when you have an area of, that's in excess of 5,000 square feet for a new or retrofit. So in 2010, January, the DoD released a memorandum basically directing facilities to implement ESA using LID in accordance with methodologies that were outlined in that document. Further clarification was extended by the Army in December of 2014, saying, that, ESA is applicable to all DoD construction projects that have a footprint greater than 5,000 gross square feet or expand that footprint of existing facility by more than 5,000 square feet. So that the overall design objective for each project is to maintain that pre-development hydrology. And we have, Army Stormwater Guidance, LID guidance that was released in 2015 of September. And we're also now required to track our pre and post results for both planning purposes, and it's rolled up and reported. ESA clearly has 3 recommendations basically for how to do that modeling. The first is a 95th design storm event. Then the second would be a continuous simulation modeling approach, such as SWIM. And then finally, the third would be continuous simulation with optimization. An example of that is sustain. There is a significant cost difference and time requirement, data requirements for these 3 modeling approaches. And that can have the potential to significantly alter your design results for your expansion, your footprint basically. So the question becomes, how do you select the most appropriate modeling approach to ensure not only compliance, but also get basically the lowest volume, the minimum volume to meet that compliance, and therefore it should be, in most cases, the lowest cost possible. And so that was what the Air Force and Tetra Tech worked on, and it was, okay, how are we going to go meet this? So they looked at the modeling approaches, and basically, how can we go and determine which of these compliance strategies would be best for an installation? You got your installation data, which for installation data, you generally are going to have your soils data, your rainfall data, and then regulatory requirements. Whether or not that is a regulatory requirement could be, like Dave said, a TMDL for an impaired watershed. Or in this case, we're focusing on ESA 438. So which is the best strategy for an installation to go with? 95th percentile, continuous simulation, SWIM, or continuous simulation with optimization? They developed a spreadsheet approach, and I'll go into that in the next slide. That spreadsheet approach basically looked at, they developed what is called STORMY, analytical elements, hydraulic conditions, and what BMP size would you have if you were to implement this spreadsheet tool that assesses minimum compliance strategies. Stormy looked at that, and it basically, what it does is it takes your preliminary installation data, you input that into the spreadsheet, and it will go out and basically do a simplified version of the 95th, the continuous simulation, and continuous simulation with optimization, and get you a cost difference, if you will see, or not a cost difference, but a volume difference here. And that translates to your surface area, your volume, and a cost. So that was the very first one. It worked very well at the installations in California where it was actually implemented. And the focus on the ESTCP now is to take that model selection tool and do 2 phases. Phase 1 would be basically how accurate does the MST determine the minimum cost or volume size compliance strategy for widely ranging climate and soils data. So we've done that. I'll talk about that in the next slide. And then our phase 2 for this project is basically do a full-on, full-scale demonstration to do all 3 of those modeling approaches at 2 installations. And how well does what the MST spit out, basically what the results from the MST, did it properly select the lowest volume compliance strategy modeling approach versus what comes out of the full-on modeling when we go and take it through sustain, swim, and a 95th design storm event. So that's what we're doing for the ESTCP project, is we're doing verification of our modeling approach selection for the model selection toolkit. So verification of that MST. What we've done is we assessed 208 installations across the United States, CONUS, from a range of all three services. Well, actually it was all National Guard, Army, Air Force, as well as the Navy. We took 208 from climate regions. We down selected to 45 installations from those 208 to do the preliminary runs with the MST, so that we can go and stress test that MST and verify that what we're getting from the MST is the correct approach. So 45 installations, they went through the model selection tool, and the model selection tool had a recommendation for which modeling approach should be used. Like I said, design storm, continuous simulation, or continuous simulation with optimization. We compare those volumes. And from that, we have a recommended modeling approach that the installation would then use to go full-on modeling with for their design. We're at the verification process now, and our objective was to obtain a 90% accuracy with the volumes that are less than or greater than 10%. So our results today are, we've done, this pie chart shows our preliminary results for phase 1, which are those 45 installations. We looked at the hydrologic soil groups, the A through D, and then a combination of all A, B, C, D soil groups. That's basically your infiltration rates. From this, the pie chart shows that we have 78% of the 225 scenarios for the hydrologic soil groups had cost difference that were greater than 10%. Of those 98% were predictive accurately. So they meet our project objectives. Now the bar chart shows the distribution of models selected across soil types, as well as where there is no match. Optimization only expected where there are heterogeneous soils, the ABCD. So basically, installations where you have high heterogeneity of your soils, that's where we had only, we had no matches for some of our MST runs that we did. So what we're doing now is we're verifying on the full scale. We're doing the demonstration at 2 installations, like I said. We already have the MST predictive modeling approaches, but now we're in the process of obtaining the data from the installations for putting in a design storm, continuous simulation, and continuous simulation with optimization. That will give us the actual volumes required to meet ESA 438, which we can then compare with outputs from the MST. And that will tell us basically if we have a consistent modeling approach that was selected with MST. So we're in that last phase of this demonstration. And the question is, why are we going through all of this, basically? What's the usefulness of the MST? And basically, the MST was envisioned to help installations determine which modeling approach that can demonstrate compliance with regulatory requirements with a minimum volume or cost of BMP implementation. So the MST is basically capable of using readily available installation data set for soils such as your SERGO, your rainfall data, and regulatory information. to basically quickly and accurately make a determination of modeling approach most appropriate for your installation. Because our overall objective was to identify the smallest volume and compliance approach without going through a tedious model setup process at an individual installation. Many times the installations are paying for full-fledged, continuous simulation with optimization, modeling for very large areas or even the entire installation in some cases, and that may not be the most cost-appropriate modeling approach to be utilizing. So the planners or stormwater engineers from an installation will be able to basically input their watershed characterizations, soils, rainfall, regulatory, into the MST, and then the MST will use that information to determine which modeling approach is the most appropriate that will result in the minimum size BMPs needed to meet ESA compliance. So it's supposed to be rapid selection of most appropriate modeling. It's going to reduce the overall modeling effort and the cost of those modeling efforts. And it should identify the approach most likely to secure more than 10% savings on BMP size so that you can basically reduce your overall cost not only for the modeling but also for the implementation of your BMPs across your installation. The other thing that we're looking at is how to increase and optimize your placement of your BMPs across your installation. And in general, we think as designers, the best place is to put it always at the outfall. And that's actually not necessarily the case. You may want to, if you're redesigning an area and you're doing a retrofit or you're doing a new construction project, your BMPs may actually go up drainage, not down drainage. And we have it ingrained in us that we do everything down drainage. And so we're hoping that this process can actually help with this. So some of the usefulness that we're looking at for the MST is, like I said, it has the capability for sizing. We're looking at implementing some tracking tools within it so that we have an Excel, it's an Excel sheet. It's pretty easy to use. We're looking at developing a GUI for navigation purposes so that we have basically a seamless integration of those detailed modeling results so that you can pick them into your GIS layer and you have a capability of quickly ascertaining whether or not you're going to be in compliance. It can also be used for tracking and accounting for historic projects, new proposals, your master planning approach, etc., so that you get the credits that you are required. And then for compliance purposes, report generation, etc. We're also looking at, developing conceptual design fact sheets, master planning, BMPs, how to link your outputs, your modeling outputs, so that you're tracking it and you can trade areas, like I said, within the drainage area so that you have appropriate BMPs and you get the lowest cost solution to not just for that project, but potentially all of your projects within that drainage area. And then project scale prioritization and selection, ranked by efficiency, effectiveness, and your multiple benefits. So these are some of the ways that it's actually the MST is being utilized for some of the Air Force installations. They're using it to track their within their master plan, where within the watershed they have development projects, what BMP sizes are most appropriate, where to put those, and what type of results they will have after implementation. And this is the tracking form that's developed for historic purposes. Optimization and BMP placement. looking at the whole watershed here, the entire watershed, where is most likely the most cost-effective area or the highest need within the darkest area would be one. So you would want to focus most of your BMPs within that dark area where you have a higher infiltration soil. And this is an example of that, where you could go and have linked approaches for, street greening, etc. So that's one way of looking at this and one of the tools that we're looking at. And this is another view of that, actually all compiled together as an output for a new master plan. And the exact same thing here is retrofits. Where should you put your retrofits? What type of retrofits should you be using based upon your soils? And you would have basically a BMP shortlist and designs for that. So in conclusion, the MST basically has the ability to inform the end user, the installation, on what is most appropriate modeling approach to use at your installation or for within the installation within different watersheds. Should you be putting in a lot of money to have high level modeling, or could you get away with a 95th design storm event? By doing this, you're going to have a significant savings seen and realized by your installation, because you're not wasting money basically on modeling to a full scale that you may not need, and your BMP size should reduce based upon your soils. And then primary benefit of this is to that end user, they'll have the knowledge to properly select, quickly ascertain whether or not they should be using one of those three modeling approaches and which one is going to most likely save them money, and that are informed before they go into contracting for an A&E firm. So ultimately, selecting the modeling approach known to generate your lowest cost or your lowest volume compliance solution could save millions of dollars in BMP construction and long-term maintenance costs across the DoD. It's going to save time, cost, by the installations providing this capability to, like I said, quickly ascertain which modeling approach is appropriate for their site conditions. And then you're also going to see more cost savings by the ability to site BMPs in more appropriate locations within the drainage areas of that activity, specifically based on soil characterizations within the drainage area of concern. If you have questions, I'm open to answer them now. Thank you.
Thank you so much, Heidi. We did receive a number of questions. Starting with the following: what are the objective functions typically used for BMP/LID placement optimization?
It is looking at the actual soils data within the drainage area to identify where you would have the highest infiltration rate. And that is the objective of it, is to place within your BMP in the most, the highest infiltration area that you can find within your footprint of that drainage area.
Great. For the 95th percentile design storm, what duration storm do you assume? Is it 24 hours? And if not, how do you obtain such a number?
It is 24 hours, and that is all outlined in the requirements by the EPA. They have the specifications for the design storm within that, and that's what we utilize. So it's generally dependent upon your rainfall data, what you have, whether you have 30-year or 50-year. 50 years preferable to 30-year.
Thank you. Can you tell us how your tool is expected to interface with other stormwater requirements beyond EISA? Most importantly, local requirements associated with LEED?
Chad Chad and we are in the process of integrating that in. And a lot of that has to do with the retention times, temperatures, what the regulatory concern is, whether or not it's, a heavy metal, sediments, et cetera. Most of our focus at the moment is on sediments. So we're in the process of determining the effectiveness, I would say, of MST for integration with regulatory requirements beyond ESA.
Great. Here's a bit of a longer question. What is the purpose for an installation to use this tool? Who is the target audience for its use? And if this tool is to be used by folks not trained in stormwater modeling requirements?
That's a really good question. The level of expertise on this is actually the knowledge base is intentionally lower because we see this more as a pre-scanning approach. And so we anticipate that landscape architects, maybe the stormwater manager at an installation, most likely, your normal regulatory group that will be doing your assessments should be able to use this very effectively.
Thank you, Heidi. What types of BMPs would you say are considered in the sizing and costing?
The BMPs that are within it are retention, detention, infiltration, bioswales, vegetative filter strips. Those are the primary ones that have been assessed and integrated into this.
Thank you. And a question from EPA. Can you elaborate on the specifics of the algorithm that MST used to determine which of the three models, STOMRE, SWMM, or SUSTAIN, were appropriate?
So well, I would have to go and refer that over to Chad because I don't have that data right in front of me, but I'm more than happy to provide it.
Great. We'll put you in touch with the author of this question so that you can follow up with them.
Okay.
Can you please tell us what data is required or elaborate on what data is required to populate the MST, please?
The bare minimum data that's required is the local SERGO data, so your hydrologic soil groups that you have within your installation, the DEM, preferably LIDAR based, and the GIS layers for the current existing development, CAD if possible for the projected new footprint, and rainfall data, precipitation data for that area. That's pretty much the minimum.
Thank you, Heidi. A few more questions, please. Can you please elaborate on the objective functions? If the objective is simply to place BMPs in high infiltrating soils, do we really need an optimization approach, or is a greedy algorithm sufficient? Can you please clarify?
Let me read that question. Okay, maybe I simplified the objective on that. Yeah, it would be to determine, one, whether or not you have soils that would be more appropriate for increased infiltration. Yeah, for some of our installations, we would have to go the full optimization because of the soil types that they have. But the MST looks, what we're hoping to find out is for those installations that have very high heterogeneity soils, where they could distribute the BMPs most appropriate so that they are not just taking care of that footprint, but possible expansion of other areas and development of other areas.
Thank you, Heidi. And now I'd like to pose some questions to both you and Dave, starting with Dave, and then perhaps Heidi, you can jump in. When and where will your modeling tools be available? You mentioned that these projects are midway. In the interim, is there a way to access these tools for interested parties, Dave?
Yes, there's, again, speaking for my project, there's a AGWA, that's AGWA, website available now. You can search on that. However, that does not have the added features that are being incorporated as part of the ESTCP project, like a pond tool for the erosion control structures. That, when we are finished with the products, there'll be a live link on the ESTCP website associated with the project to where all the training materials will be, as well as the code and the tools itself.
I'll reiterate some of what Dave said. Our tool will have the directions for where they can obtain it from the ESTCP website. We plan to actually have it housed within our Net Zero Planner, which is based out of Searle, for the DoD to access.
Thank you both. In terms of the level of expertise required to run these modeling tools or use them, what sort of knowledge is needed? Starting with you, Dave, please.
Our target audience, and this is based on experience with burn area emergency response teams and other training sessions we've done, is a basic level of GIS skill within ArcInfo or our ArcMap, and a natural resources background, but not necessarily a specific hydrologic modeling background.
That's exactly the same with us. I mean, ours is developed for, like I said earlier, planning level, so it could be used at design, or it could be used out of environmental office on an installation. So.
Great, thank you. Will we get finished versions of the certifications of networthiness? This is from Fort Drum.
Dave here, we do have a certificate of networthiness for AGWA already.
Ours is in the process, going through the Net Zero Planner, that it should be done through that process. We have not obtained ours yet.
Do you expect it fairly soon, Heidi?
Sorry, what?
Do you expect the certificate fairly soon, or certification?
By the end of the project, which will be like in a year and a half. We're in the process of doing it, so yeah.
Wonderful, thank you. And before we wrap up, what is the single most important take-home message that you'd like to leave with our audience today, starting with you, Dave?
Buy rain gauges. I know that may sound a bit facetious, but in terms of doing a decent job of model simulations, if you don't get the inputs right, you're not going to have a chance at getting the outputs right.
So when you say buy rain gauges, how many? Is one enough for watershed modeling?
Oh.
No, well, not necessarily. It depends on the size of the watershed. If you're, and don't want to speak for Heidi, but if you're looking at a small project in the cantonment area, one rain gauge is enough. If you're looking at a 50 to 100 square mile watershed, one is probably not enough.
I can't I completely agree with Dave, and I can't express the need for rain gauges and flow gauges throughout a watershed, not at just at the outfall, basically. The more you have, the better it is. I think the other thing, for at least for our size of it, is the MST is, you know, this is a preliminary scoping tool, and you know, there are many questions needed to be asked by the installation prior to going out for contract to have hydrologic analysis done for their cantonment area. And knowledge is your friend on things, so that you know you're doing the best job that you can.
Great. Thank you both for a great webinar. Our next webinar is on Thursday, January 14 in the new year, and it will focus on vapor intrusion. We will have two speakers. One will give a regulatory update, and the other one will talk about advances in assessment tools. The speakers will be Dr. Helen Dawson, formerly with EPA and now with Geosyntac Consultants in the Maryland area, and Dr. Todd McAlery from Geosyntac in Guelph, Canada. I hope you can join us. Registration is open. Just go to the SERDP and ESTCP webpage, and you can register for this free event. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. At this time, we would appreciate it if you can please take a moment to complete the brief survey that will pop up on your screen to help us in future planning of these webinars. This concludes today's webcast. Thank you very much.